Atoms are the building blocks, but it's kind of important to remember the four really important elements for biology, which are carbon, hydrogen, oxygen, and nitrogen. Okay? We also have some elements that are trace elements, and the two pictures down here we're showing you that if you have a deficiency in a trace element, it can still lead to really, really bad problems, even though you only need a little teeny tiny amount of that particular element. Okay, so I think that's mostly a review from bio for you guys. Elements on the picture below. So in this one, you have, you know, a representation of an atom. That means you have 9 protons versus 3 protons. But what elements would those be referring to? My giant periodic table is behind you guys, but what element has 9 protons? Okay. Fluorine. And what element has 3 protons? Lithium. Okay. So this is supposed to be an illustration of a certain type of compound. I want you guys to see if you remember what type of compound this would be. What does it look like happened with the electrons? Because you need to think about what a neutral lithium and a neutral fluorine would look like. I'll give you guys. So if you count up the number of dots around there, there's only 2. It's not like where I'm pointing at all. There's only 2 on the lithium now, but now there are 10 up here. So remember that when you have an uneven number of protons and electrons, that you have a charge forming. So you have this now has a -1 charge because it has 1 extra electron, and our lithium has a +1 charge because it lost an electron and now has sort of an extra proton. Okay, so what type of bond will this be if we have electrons being transferred? Adrian?
I think it would be ionic.
It is ionic, yes. Oh, let Jason in, please. Okay, yes. So this is a covalent bond because, as you can see here, we're looking at electrons being shared. So the element in question down here is still fluorine, and if that one only has 1 proton, that's hydrogen, okay? So just as a quick review of your chemistry nomenclature, this one over here would be called lithium fluoride, and this one would be hydrogen, that's an E, monofluoride. You might remember that HF is also a formula for the acid, hydrofluoric acid, but because it's not dissociated, it's the hydrogen monofluoride molecule. We're going to talk about the different types of bonds that form between different things. So ionic bonds occur between things that make an ionic compound. Covalent bonds occur between things that make a covalent/molecular compound. But I want to make sure that you guys know how these molecules stick together. So this top example, what is this top molecule probably if it looks like Kermit the Frog? What do you guys think it is? This, I'll give you a hint that the charges would be like this, if I can draw. I can't draw. The little things are positive and the big thing is negative. Water, I heard somebody say. Okay, so these are, this is why they look like Kermit, kind of. I'm not doing the greatest job there, but. So those are your hydrogens, and the bigger atom is your water. Okay, so what we're looking at here is going to be specifically a type of bonding that we need to talk more about. But before we get there, what type of bond holds the hydrogen to the oxygen? So what bond is, let me point, what bond is this? Is that ionic or covalent? Okay, that is covalent. Okay, so that's true. But then what kind of bond, because the oxygen is negative, what kind of bond is this? This is what we should have been reading about with both chapters. That, like if we're talking about sticking this negative thing over here to this positive thing, what is that? What'd you say? That is a hydrogen bond, yes. Okay, remember a hydrogen bond is not within a particle, it is between multiple particles. Okay, so that's going to come up when we talk about water again. Okay, other things that can happen. So looking down at the next molecule, our oxygen is still negative here, and our hydrogen is still positive. Another way you can show that is by drawing an arrow with a plus sign on one side, so that indicates that the hydrogen is the positive side. But then when we're looking at the ammonia, if you remember your bonding very well, what is on top of that nitrogen that's not pictured? Go ahead. Valence electrons, yes. There are 2 dots up there. If I can draw them, that would be helpful. Okay, so whenever you have a lone pair, that's going to make that side more negative. So as you see in this particular scenario, you have 2 negative things kind of going together, right? So what's going to happen when those molecules come close together if they're both the negative sides? Think about magnets. They're both the negative sides, so they're going to repel, right? Sorry. So that's repulsion. Okay. Lastly, what type of bonding is this then between these hydrogens and oxygens down here? Okay, so the sort of same thing still applies, except that I drew that wrong. Oh, go away, I don't want that there. Sorry. That's supposed to be a plus. And then this one would be a minus, okay? So if you're looking at your oxygens and your hydrogens, you have positive and negatives attracting each other again. And what type of bonding is that going to be? Based on our example at the top. That is also hydrogen bonding. Okay, who remembers really quickly the 3 elements that hydrogen bonds with in order to be really considered hydrogen bonding? Oxygen is one. Nitrogen. And fluorine. Very good. Okay. If it's not one of those 3 elements with hydrogen, it's just a dipole-dipole bond. So it's just a polar bond. All you need to remember from chemistry regarding energy is that when you break bonds, energy is released. And when you form bonds, energy has to be absorbed in order to do that. Okay, so other than that, we're fine. As you know, water is incredibly important for life. It is basically the solution of life, and that's actually what I wanted to make sure we pointed out. So keeping in mind, because we are so composed of water, all of our chemical reactions are essentially involving aqueous reactants, because everything's dissolved in the water of our bodies, of our cells, okay? So that's kind of an important thing to remember. Water is also really cool because it's one of the few things that exists in all 3 phases, and we will talk about all of the emergent properties again. And like I said, I know a lot of those are kind of a review. I mean, I know you've heard the emergent properties of water quite a bit by this point, but again, we're kind of taking a certain, very specific look at them. So too fast, let me know. Okay, this is basically the same picture that we've already had. So again, you've got your little teeny tiny hydrogens. I'll label them actually with the letters this time if that helps. And your bigger oxygen atom. And does anybody remember then what shape this molecule is? It is bent. I feel like I try to beat that to death, so I feel like you've probably heard that before. Okay, also remember that it is polar. And again, if you want to add your little arrow that side's the oxygen's the negative side. I mean, it's kind of obvious by this point. Looking at these down here, these little deltas, that's actually showing the same thing. You'll notice that it's showing the same thing as the arrow. So the negative side being the oxygen and the positive side being the hydrogen. That's another way in chemistry to indicate partial charges, and that's all that's showing you. It's just saying that side's more positive or that side's more negative. But just as a review one more time, what is this thing in here? What is that interaction? That is a hydrogen bond. Okay, and remember one more time in there, that is a covalent bond, and specifically a polar one. All right, any questions there? Cohesion and adhesion, just remember things that are cohesive. When you're a cohesive group of friends, that means you all stick with each other. When you are adhering something, that's because you are sticking something to something else. So cohesion is all water molecules stick to each other because of that hydrogen bonding. Adhesion is when water molecules stick to something else, like the inside of a xylem cell, which is the example on the right. Okay? So we talk about cohesion and adhesion quite a bit right now, and then we talk about it a lot when we talk about plants, because that is the major thing that allows transpiration to happen. So it'll come up again later. And again, that's due to the bonding that's occurring here. So you can see that there's the cohesion is the hydrogen bonding in between, and basically your adhesion is when it attracts to the whatever surface you're on. So since water has both a positive and a negative side, it can stick to a lot of things. Okay? All right, for high specific heat, remember that specific heat capacity is the amount of heat that it takes to change, technically to change the temperature of something by 1 degree Celsius. Remember that unit was joules per gram degree Celsius, as you see up there. So water's is so high because hydrogen bonds are very hard to disrupt. But the reason that it's important for biology is because A, it acts as a temperature buffer, especially when you have very large bodies of it, such as in lakes and oceans and other bodies of water. But also it's important for evaporative cooling, so any organisms that sweat. When the water molecules leave sunning Santa over here, I don't know if he's Santa really or not, but so when water molecules leave him, they take the heat with them. Okay, so when they evaporate, they take the heat with them so that that cools down sunning Santa. Okay? Ice floating is a really weird thing. We all take it for granted because you've seen it your whole life, but it's not normal by any means whatsoever. Everything else is more dense as a solid, just about. Okay, but water is not. And the reason that that happens is because when water is actually solidifying, it forms this lattice structure. Okay? So as a liquid, the water molecules can all move past each other and flow around, which is what liquids do. But when it freezes, those hydrogen bonds actually become very rigid, and they form, like I said, this lattice structure, which has a bunch of space in it. And so that creates essentially little air pockets that allow the ice to float. Okay? Remember that that's important for bodies of water also, because otherwise all the little fishies would get frozen in blocks of ice if the ice were to go from the bottom up. Okay, we're going to need to spend a little bit more time probably on the solvation part of things, so that's why I skipped through the other ones a little quicker. There is no 100% universal solvent, but water is really, really close, because if you do remember from chemistry, it's very good at dissolving ionic things, and it's very good at dissolving polar things. So water dissolves almost all the things. It does not dissolve the nonpolar stuff. I think that this picture is pretty cool because it's showing how water will surround something, and this is literally how it quote-unquote dissolves. It gets surrounded by molecules, and then that allows it to like be pulled into solution. Okay, so back to dissociation. Again, this is going to be important for your CO2 lab because this is where pH and buffers and stuff come up. So this is the dissociation of water. You might want to either sketch the picture or you can write out the reaction, which would be H2O giving you H3O plus and an OH minus. So I guess technically that's 2 waters. That's why there are 2 there. Okay, so you can either draw the picture or write the reaction, whichever works better for you. I do want you to know the word hydronium as it says it below. So that's your hydronium and that is your hydroxide. Ugh, sorry, I'm on the edge of my iPad. This is difficult. Okay. The thing to remember about pH, we discussed pH briefly yesterday, but just remember anything that has lots more hydrogen is going to be more acidic. Anything that has lots more hydroxide is more basic because water occurs in this equilibrium. So water is also crazy because it exists as a molecule. It also exists as a mixture of hydronium and hydroxide ions. So you actually have all 3 of those things floating around in your water bottle at a given time because that happens on its own. It's the self-dissociation or spontaneous dissociation. Okay? So the reason that an acid or a base gets categorized as such is because when you add an acid, it has a lot more hydrogen stuff, so it's going to tip the scale over to the hydrogen side, thus making it more acidic. Okay, so regardless of if you're adding an acid or a base, you're really talking about the balance between the two. A couple practice things for that in just a second. This up here, which is I guess kind of small, is an example of the blood buffering system. The blood buffering system, the one that's involved in CO2 exchange. So this is basically the reaction. So when you have when you're blowing out your carbon dioxide, this is, oops, now I've got to switch tools, sorry. This is the stuff that's going to be turning the BT yellow. Okay, so the main thing to write down is resist pH change. So it's something that you add in order to resist pH change. The reason we have the bicarbonate buffer system is so that when you do have things generated in your body that are going to lower the pH, you're able to not get sick from that, essentially. So as you can see here, you know, you've got your CO2 is a reactant. When it mixes with the water of your body, the water in your cells and everything, you are creating this acid, okay? But your blood is able to convert that back to this, which is going to allow you to then recycle it and bring you back to having water and CO2 again, okay? I really kind of want you guys to look that up a little bit for yourselves tonight, and we will talk about it again some more tomorrow. But I do want you to look into that because, again, it's part of what you need to say in your lab report. Let's see.